Thanks for coming. Thank you to the organizers for organizing everything. Today I'll tell you about a recent work of ours that's going to appear in the coming Fox. The title of our paper is Random Order Set Cover is as Easy as Offline. This is joint work with Anupam Gupta at CMU, Greg Keeney at Harvard, and I'm Roie from CMU as well. All right, so let's jump in. Let me describe the problem to you. So what's the set cover problem? You're given a collection of n elements, which I'm calling script u. You're given a collection of subsets, which I'm calling script s. There's n elements and m sets. And your goal is to pick the smallest number of sets to cover all the elements. For example, in this picture, the dots are the elements, the ellipses are the sets. And this is a potential feasible solution to the problem. Great. So what's the online version of this problem? By now, this is somewhat of a classic problem. It was introduced by Alon, Auerbuch, Hazar, Buchbinder, and Naor, coming on 20 years ago. And in this version of the problem, we're again solving set cover, but this time we don't know any of the elements up front. And instead, they're going to be revealed to us one by an adversary. So we can think of this as an adversary fixing the ground set of the elements and then showing it to us one by one. So the ground set is unknown. Now, the hard part is that as soon as an element arrives, we have to immediately pick a set to cover it, and our decisions are irrevocable. So once we buy a set, we bought it forever. So for example, the adversary might first give us this element. We pick this set to cover it. We get this element. We pick this set. A third element arrives, and perhaps it's already covered by the sets you've bought, so no need to do anything. And maybe this happens again. And this game continues. And your goal is to get a near minimal solution despite the fact that you don't have foresight. And you're competing with the offline optimum that has full information about the future. Okay, any questions? Good. So what's the random order version? Well, it's the same thing. So an adversary, again, is going to fix an unknown ground set. The only difference is that this time the adversary is forced to roll some dice and then shuffle the order of the elements uniformly at random and then reveal the elements in that uniformly random order. So for example, if this is the ground set that the adversary fixed, and I'll stress that this is an unknown ground set, the adversary then sort of is forced to pick this random order and then reveals the elements in this order, and we play the same online set cover game as before. The question we answer in this work is random order more like offline or more like online?
So just to make clear, how are the sets given?
Good. So at the beginning, you just get these like labels. So you'll just see empty sets at the beginning. And then every time an element shows up, it tells me I'm part of sets 1, 3, and 7, whatever. Yeah. Good. So the title of the talk maybe gives away the answer, but we'll pretend that you're in suspense. So what's known for this problem? Surprisingly, nothing. So somehow this question has been overlooked as far as we know. So offline, you can get a log n plus 1 approximation. Okay, this is a classic result that's taught in approximation algorithms courses. The simple greedy algorithm, for example, achieves this bound. In adversarial order, so this original paper and like a long line of follow-up work showed that you can get a log n times log m approximation, even despite the fact that you don't know like anything about the ground set, which I think is sort of amazing. And this is the right answer. So we also know lower bounds. Yeah. Okay, so I'll mention one more result, which I'm calling the stochastic model. So in this model, you're given a known distribution over elements, and then you're sampling n elements from this distribution. Now the support size of that distribution might be much larger than n. Okay, and so in this paper by Anupam and some co-authors in 2008, they showed that you can get a log m times support size for this stochastic version. I'm kind of not giving them enough credit. Their algorithm also satisfies some additional requirements, which are very interesting. So their algorithm is oblivious in a very strong sense. But at least like in this language, like this is the bound that they achieve.
Support size could be suits above.
Yeah, exactly. Yeah, but yeah. Okay, so there's some reasons you might believe that you can't do better than log n times log m. Just because the algorithm for the adversarial case is like very natural, it's become this natural primitive in a lot of online algorithms today. And we'll talk sort of why this was kind of a natural barrier. But we show in our paper that in fact there is a randomized polytime algorithm for an even more general problem, which I'm calling the random order covering IP problem, with expected competitive ratio order log mn. So at least in the regime where M is poly n, this matches the offline bound. Okay, yeah.
I mean, does it have implications on the stochastic setting?
Yeah, it's so you can exactly. So you can think of this as basically the stochastic setting, but with an unknown distribution. Like up to like sampling with replacement, which doesn't really matter. Yeah. So in fact, this is not just like a new analysis of an old algorithm. This is a new algorithm. And essentially what we show is that it's possible to learn the distribution. I don't know if you can see what's written here. On Zoom, you can see it, but yeah. So we show that it's possible to learn the distribution while you're solving the problem without taking too much of a hit. Okay, any questions? All right, so let me just, we're going to focus on set cover for the rest of the talk, but I just want to say what the covering IP problem is. So an adversary is going to pick a covering IP of this form. Okay, so some constraints A1 through N. I think N is the number of constraints, and the dimension is fixed. We're in dimension M. And the adversary rolls dice, and these constraints are unknown, and then we're fed them one by one in a random order. And the goal is to maintain a feasible solution to this IP, even as the constraints arrive online, with the constraint that our solution must be monotonically increasing. Okay. So set cover is the special case when the constraint matrix is 0, 1. It's kind of a nice sandbox to understand things. Okay. So that's basically the intro that I wanted to give. Any questions thus far? Good. So in the rest of the talk,
yeah, so I didn't quite get, so you say you're going to get a log m times n sort of approximation, and I guess the m is unavoidable, or? Yeah,
so actually, good. So m over log m is unavoidable for sure. Yeah. Okay. So basically, yeah. And that's an information theoretic bound. Even in random order, yeah. It's actually not ours. You can adapt, like this is a known lower bound and it works in random order. But it's in the paper. Okay, sorry. All right, so in the rest of the talk, I'll spend a little bit of time discussing previous work, namely the Alon et al. Paper, just because it kind of gives nice context. It's just good general knowledge. I'll then tell you about our algorithm. I'll start with the algorithm is called learn or cover. I'll start with a nice exponential time version of it that's particularly kind of clean and simple. Then we'll move to the polytime version, and I'll end with a discussion of some extensions and lower bounds. Okay. So roughly how the Alon et al. Algorithm works, it's a two-stage algorithm. And stage 1 consists of solving the LP. Stage 2 consists of rounding the LP. So classic kind of approximation algorithm paradigm, only online. So here's the classic LP for set cover. We have a variable for every set, which denotes how much we've selected the set fractionally, and we have a constraint for every element in the ground set, and we want the fractional number. Fractionally, we want at least one set covering that element. Right. So what they show, and this really has become like an important primitive in online algorithms, is that even if the constraints are arriving online, you can maintain a log m approximate solution to this problem, and such that your solution x, which is fractional, is only monotonically increasing. Okay. Now, this is a really nice property because it allows you to round online. So what do I mean by that? Here might be my LP vector at time t, and at time t plus 1, it changes by this delta. And because it's monotonically increasing, these deltas are only positive. And so what I can do is I can take each coordinate with probability only proportional to the delta. Now, if you think about it for a moment, you can convince yourself that you can do this in such a way such that at any time t, the probability that I've taken the set S by time t, sort of over the entire run of the algorithm until time t, is equal to its LP value at time t. And so basically, you can think of rounding as being performed at the very end of the process. Like I can sort of like separate in my head like the online solving and the rounding process, and it suffices to analyze random, independent random rounding as if it were performed offline. So basically, like if you didn't follow this, like the point is that you can think of solving the LP online and then performing like the rounding to an integral solution at the very end of the of this online process. So how do we do independent random rounding? every element is covered with constant probability. We boost this, by repeating log n times and then union bound over the elements. Okay, so this algorithm gives a log n log m. Log m because I'm losing log m from the fraction from the approximate solver, and then log n from the union bound from the rounding. Good. Okay, one more slide about the solver. Just it's just nice. So here's the world. These are initially the sets. So initially they're empty. We don't know anything. The algorithm is kind of the natural thing, or it's a natural thing that you might try. You initialize the kind of fractional value of the sets to something small, and then when an element arrives, an element v arrives, and while it's fractionally uncovered, you just sort of repeatedly double all of the values, the LP values of the sets covering it until we're feasible. Okay, so maybe this element arrives, and we'll start sort of repeatedly doubling the values of the sets covering it until it's fractionally covered. Another element arrives, we need to do this again, and so on and so forth. So maybe this is the way this works. Okay, how do they analyze such a thing? The classic primal dual method. So that's really the entire algorithm. But for bookkeeping, we'll imagine that every time we do this sort of doubling for the primal variables, we also add one to the corresponding dual variable. Okay, so in the dual of the set cover problem, there is a variable for every element. Okay, and then you show kind of 3 simple lemmas, which are a nice exercise. Classic primal dual stuff. So the primal solution is feasible, the primal costs less than the dual, and a scaled down version of the dual is also feasible. So I just want to highlight this was an elegant algorithm that was sort of conceivably kind of the natural correct thing to do even in random order. In fact, I learned about this in an exercise in a homework. So that's how classic this has become. Okay, good. So neither stage of this algorithm can be improved in random order. So if you think about it, independent random rounding has to lose log n. There are situations where you will, if you do this, you will always lose the log n factor. And we show in our paper that if your goal is just to get a fractional solution, you will lose log m even in random order. Okay, so basically this is saying that the 2-stage analysis of maintaining a fractional solution and rounding it is doomed to lose log m log n. You could still wonder if maybe that's just an analysis artifact, but we also show that no, it's actually the algorithm is fundamentally kind of not sufficient. There are situations even in random order where you get log m log n. All right, so a new algorithm is needed. And one way to view our algorithm is that we're never really solving the LP, only kind of. So we're going to maintain something like a coarse solution to the LP, except it's not really feasible nor really monotone, and yet can be rounded gradually over the course of the algorithm to get the bounds that we claim. Maybe this looks mysterious, but I'll explain what I mean by this. Any questions? All right, so let's dive in. Okay, so I'm going to give you a very simple algorithm that actually makes no mention of LPs. We're going to be in the unit cost setting, and we're going to operate with exponential time. So yeah. Okay, so here's the algorithm. So in our heads, we're going to think of these 2 collections. One is U, which is the ground set of all elements that we need to cover. That's the world. And we're also going to imagine holding on to a portfolio, script P, which is, so script S was the collection of sets that I can pick, and K is basically the size of opt. You can assume using standard guess and double tricks that you know the size of opt. Okay, so P is all possible K tuples of sets. It's every possible solution that could be the optimal solution. Initially, you don't know anything. You haven't seen any of the elements. You have complete ignorance. Every subset of size K could be the optimal solution. Okay, so here's the algorithm. At time T, an element arrives. If it's covered, do nothing. Okay, so far so good. If it's not covered, we'll do 2 things. We'll choose a T uniformly at random from P. So recall the type of T is a K tuple of sets. And then what we'll do is we'll buy a random set from this K tuple. And this is all uniform sampling. Okay, the second thing we'll do is that we'll prune this portfolio. Any K tuple that does not cover the incoming element, we know definitely it's not the optimal solution because the optimal solution is feasible. So let's prune it. Now, you might complain, why should the set R cover the incoming element? Right? The requirement was that I be feasible at every stage of the algorithm. Okay, it won't be. So what we'll do is we'll also buy an arbitrary set to cover this incoming element. That's it. That's the entire algorithm. Okay, we want to understand its cost. And rounds in which an element arrives and is covered, we incur no cost. Round in which it's covered, it arrives and is uncovered, we pay 2. One for R and one for this arbitrary backup set. So we just need to count the number of times we land in this else clause, right? All right, great. Case analysis. So case 1, at least half of the T in this P cover at least half of U. I'll let you stew with this for a sec. So basically, half of the potential solutions in our portfolio are decent. They cover a good fraction of what remains. Case 2, the opposite. At least half of them are bad. Okay. In case 1, I claim that R covers at least size of U over 4K in expectation. Why is this? Well, if I draw a T uniformly at random, right, like half of them cover at least half. So the expected coverage of T is like a quarter. And then there's K things in T. So I'll get like 1 over K in expectation. Okay, so this means that U is going to shrink by 1 minus 1 over 4K in expectations. You have to deal with these expectations, but this is not an important part. Okay, case 2, at least half of these T's are bad, right? They cover less than half of what remains.
And you also prune.
Yeah, you're pruning U. Yeah. I'm just simplifying notation. Absolutely. So when I say covers half of U, I mean the uncovered part of U. Yeah, thanks. Good. So the element V is coming uniformly at random, right? I'm conditioning on it being uncovered. And so it's coming uniformly at random from the uncovered part of U. And so if T covers less than half of U, then it's going to be pruned with probability 1/2. This is where we're using random order. So this means that I'm throwing out about a quarter of my T's from P in expectation. And so P is going to shrink by like 3/4. We're basically done. So why is this? Okay, so sorry. So the picture you should have in your head is that you start with these two objects, and you don't know which case you're in. You can't actually evaluate how much of U you've covered because you don't know U. And these things are in expectation, so you don't know if you're really in case 2, but we agreed it's an exhaustive case analysis, or in one or the other. And so no matter which case you're in, you're taking a bite out of one or the other of these. All right. So let's suggestively call case 1 a cover step and call case 2 a learn step. So U is initially of size n. How many times do you need to shrink n by 1 minus 1 over 4K until you get to a fraction? Well, K log n. So after K log n cover steps, I've covered everything and I'll never incur costs again. P is initially all tuples of size K. So it's of size roughly m to the K. How many times do I need to shrink m to the K by a constant before I've identified the optimal solution? Well, K log m. So after the sum of these things, K log m plus K log n, i.e. K log mn, I've definitely done one or the other, and so I'm done. That's it. Questions?
Is it max?
Yeah. Well, no, it's some actually. Because you need to have done one or the other. With the max, I might be splitting the max between the two, and that's not good enough. It doesn't matter, yeah. But just to make sure we're good. Okay, so big question. So we figured this out first. This is the history. And then the question was how to make this polynomial time. And can one reuse this intuition that you're either making progress learning or covering? So what's the exponential time part of this, right? It's you're maintaining this enormous portfolio of all possible sets. You're enumerating all possible solutions. But why do you need to do that? Well, you're using this enumeration to generate a distribution over sets. And so the natural thing to try to do is to directly maintain a distribution over sets without going through this enumeration. And that's exactly what we do.
Actually, can you just say something about you don't lose anything at all by guessing, like K?
Oh, you'd lose 2.
A factor of 2. That's
Yeah,
it.
but basically, as soon as my solution has exceeded, I set myself a budget of K, and as soon as I've identified, I'm allowed exponential time here, so I can even say, I can even look at the optimal solution on the current set, and as soon as I've exceeded 2 times what I allocated myself, I recompute from scratch. and I get a geometric kind of behavior in my cost. Sorry, the
Uh-huh.
question was, oh, you're asking, good. I don't have to repeat the question.
Oh, I mean,
Yeah, sorry.
yeah,
Did that answer make sense? Or
I think so.
I can, it's a sort of standard trick. I can explain it.
Yeah,
also.
sure,
Yeah.
sure. Thanks.
Okay, so let's move to the polytime version. And let's stick with unit costs. I'll say a brief word about how to do this for general costs, but most of the talk will be about unit costs. Okay, so we're going to do exactly what I said, which is maintain a distribution directly. We'll start with a uniform distribution. Okay, we initialize a distribution over sets to be the uniform distribution, reflecting the fact that we don't know anything. At time t, an element v arrives. If it's covered, do nothing. All right, we could expect that much. And we'll do something very similar to what we did before. So buy a random set from this distribution. And now for every set covering the incoming element, we should learn from this element that showed up. Let's give a boost to all the sets that cover the element. So let's multiply their probability by E and then renormalize so that we stay a distribution. Okay, so maybe we can talk about this after as well, but this means that X is like, if we're thinking of X as a fractional solution, it's very much non-monotone. And this is a big difference between this work and the previous algorithm. So the renormalizing is making the behavior very, very non-monotone. And finally, buy this like backup set to cover V if necessary. Okay, so once again, we need to count the number of times we land in the else clause. And last time we had this very clean, case 1, case 2, and we're either in case 1 and case 2. We're not quite going to be able to do that, but we'll do the next best thing, which is to write a potential function that captures, how much of learning and covering we've done. And so here's the potential function. I hope you can see this. So phi, which is a function of the state of the algorithm at time t, is basically the KL divergence between the optimal solution. Can you see this? You can look over here if, yeah. So it's the KL divergence between the optimal solution x star and xt. And okay, so I've really scaled down the optimal solution so that it's on the simplex. So I'm thinking of it as the uniform distribution over the optimal integral solution, and our distribution xt, plus log of the number of elements you have remaining. So the red part is capturing like how much we've learned about the optimal solution, and the blue part is measuring how much we need to cover. And what we'll show, UT right is the uncovered elements at time t. We'll show that this potential, okay. So here's, by the way, the KL divergence. If you're not fresh on this stuff, we'll do a calculation in a moment. So if we can show that the potential decreases, we're essentially showing that you're kind of simultaneously making progress either in like approaching the optimal solution or in solving your problem, which is covering what remains to be covered. Okay, so as one usually does in these potential function proofs, you need to show that the initial potential is not too big. In our case, it'll be something like log mn, and it never goes below 0. We'll skip this. And then the second thing that you need to show, and this is the interesting part, is that when V is uncovered on arrival, meaning that you'll have to pay something like 2 to cover it, then the potential will decrease by a sufficient amount. So K was our guess for opt, basically. And so if you can show that it decreases by something like 1 over K, then this means, it starts at log mn. It means after K log mn, rounds of paying 2, you'll be done. And so your costs will be opt times log mn. Okay. Notice that the blue part, the log ut, only depends on which sets we've sampled R. So
if then C1 is 1 over K, shouldn't this KL be K log L?
so the C1 and C2 are just constants. Oh, sorry. So the question was if C1 and C2 should be K. You can set them to be K and then show that this decreases by a constant. It's sort of aesthetically.
Like X, this sum with X or S would be K log L. Oh, it's like a sum over like.
The question was if the KL should be
K log L or not.
K log M. I'm normalizing everything to make it.
Okay, fine. So X.
Yeah. I might need to do a calculation but I'm happy to talk about it. But I think it works. Yeah. So actually in the weighted setting we don't normalize to the simplex. It's just cleaner. But it's So okay, we'll work it out. Okay. So what I was saying is the blue part actually the decrease in the blue part in a single round only depends on which set we sample. It doesn't depend on the incoming element. On the other hand, the red part doesn't depend on which set we sample. It only depends on the uniformly random element that's arriving. Okay, so we're going to bound the decrease kind of separately. And this is where we're really using random order. Okay, the decrease in the KL divergence is really like crucially exploiting the fact that the element is kind of a uniform sample from what we haven't seen yet. All right, this is my one slide of algebra. My maybe ambitious goal is to do the entire proof. I think we can handle it. It's going to fit on this page, but the important thing to retain is kind of the conclusion at the top. But let's try. Yeah, I like the calculation, so I think we'll manage. Okay, we want to bound the decrease in the KL divergence, right? So KL divergence decrease is KL divergence after minus KL divergence before, which is this. Okay, yeah.
Okay, now I think it's X star S is like 1 over K, is an indicator. So X star is like the indicator vector of up with 1 over K. So
Exactly, I'm sorry, yeah.
Now I'm fine.
Good, yeah. Good, yeah, so I want my distribution and op to be on the same scale, so I've normalized, yeah. Okay. So you can simplify this, right? The way logs work is I get a sum over S of X star S log of the ratio of solutions at successive of XS at successive time steps. So XST minus 1 divided by XST. So how do I update XST minus 1 to XST? Well, if the set S contained the arriving element, I give it a boost of E. But in any case, whether or not it contains the element, I divide it by the normalizing factor Z. Okay, so the normalizing factor should be in the numerator of this ratio, and the E should be in the denominator, but only for sets containing V. So I get sum over S, X star S log Z minus sum over S containing V, X star S log E. Now, log Z no longer depends on S. And so we've said, per Ola's question, that X star is a distribution. So in fact, this sums to 1. Log E is also 1, so I get this nice clean expression, log Z minus sum over S containing V of X star S. What is Z? Well, it's my total kind of mass after I've done this multiplying by E. So every set gets XST minus 1, and then the ones that got a boost get an extra E minus 1. Okay. Again, we're maintaining the invariant that X at any time is always a distribution. So this sum, like sum over S of XST minus 1 is 1. And this last part, so the sum over S containing V of X star S, recall X star is the optimal solution. So it's feasible and it's scaled down to be a distribution. There's K things in the support. So it covers every element to extent at least 1 over K. Okay, and there's a negative sign, so we can bound this above by this expression. Okay, we're almost done. Now we're just going to use this nice approximation. Log of 1 plus Z is less than Z, at least for Z greater than -1, I think. And then take expectation over V, and we're finished. Do we see this? So the log and the 1 plus go away, and then we get exactly this expression up top. Okay. All right, almost there, halfway. How do we bound the decrease in log U? Well, it's log U after minus log U before, and I've rewritten it this way. So this is log UT divided by UT minus 1, and then I've added and subtracted 1. The reason I've done this is so that I can use a similar approximation to before. So log 1 minus Z is less than negative Z. And so I can get rid of the log and the 1. And now I'm pulling out the UT minus 1 in the denominator. And the numerator is the difference between UT minus 1 and UT. So recall, UT is the set of uncovered elements at time t. So the difference in these things is basically the number of elements that were covered in round t, i.e. the size of the set R intersect UT. Okay, a fancy way to write R intersect UT is the sum over V and UT of the indicator of whether or not they're in R. Okay, we're almost finished. Let's take the expectation over R. So if we take the expectation over R, we're just summing over R, XR, probability of getting R, and then times this expression. So far, so good. Rearranging the order of summation, just flipping these things, we get that this is 1 over size of ut minus 1, sum over v in ut minus 1, sum over r containing v of xr. This 1 over size of ut minus 1, sum over v, is just the expectation over a uniformly random chosen v from ut minus 1. So that's it. That's what we were trying to prove. Okay. If you've blacked out during the calculation, this is a good time to come to, because we don't really need this. This is just sort of for, so you believe me that we can prove these things. Really, what we just need to retain is what's at the top. Okay, so we've proved these two things, that the red part of the potential decreases by this much, the blue part of the potential decreases by this much. And you'll notice that they look very similar, right? The positive part of the red term looks a lot like the negative part of the blue term. And this was intentional, because basically, if we scale the blue part up by e minus 1, we get that it perfectly cancels out the first part of the potential. And we get that indeed the potential decrease, the expected potential decrease, is exactly minus 1 over k, which is what we wanted to prove. Good. So, right. So what's interesting is we can't actually say for sure that the red term decreases in every round, nor can we say that the blue term decreases by enough in every round, but somehow they fit into each other nicely like puzzle pieces and get the bound that we claim. Okay, so as I said, so the initial potential is loaded up with something like log mn. And so after k times that many rounds, we'll have finished. Any questions? Okay, so we've done the hard part. Now I'm gonna philosophize a little bit, and this stuff is a little vague, but I think there's some suggestive connections that I wanna think about that we're still sort of exploring. So let me say what I mean, and then we can discuss. So one perspective is I want to compare this algorithm, this learn or cover algorithm, to the classic adversarial order algorithm. So one can think of that algorithm. This sort of view was made explicit in this recent paper. This is this K-servers with a smile paper, if you've seen this. It's as follows. So this is that algorithm I showed you at the very beginning, the Alon et al. Algorithm. When a new constraint arrives, you were feasible previously. What you're going to do is you're going to project in KL onto the feasible region. So you take the min over points in the new feasible region of the KL between your new point, I think, and your old point. Okay, and you do this kind of projection. That's one way to view their algorithm. What's our algorithm doing? It's doing something similar, but not quite. So instead of fully projecting onto the feasible region, it's just doing a nudge towards the feasible region. Okay, in fact, you can think of it as almost doing a projection, but we're multiplying every set containing the element by e, but not repeatedly. We're not doing this until we're feasible. We're just doing it one time, and then we're projecting back down onto the simplex, which the simplex in the algorithm I gave you, we scale down opt to also be on the simplex. So we can think of this as normalizing to the constraint cost equals cost of opt. And then as we're doing this nudging and projecting, we're sampling continuously through this process, and somehow this is giving us the bounds that I claimed. Okay, so that's one perspective. I don't know if it's useful, but it's a nice view of the algorithm. And here's another perspective, which I confess I don't yet know if this is spurious or really there's something deep going on here. But let's define the function f as follows. So it's a function of fractional vectors, and it's the sum over all elements of the max of 0 and 1 minus the sum over s containing v of xs. Okay, so what is this? If v is fractionally covered, then this is 0. Otherwise, it's the fractional uncoverage. Okay, so intuitively, we kind of want to minimize f in the smallest number of steps. Maybe if we pay 1 every time that we kind of move in x, then we're interested in basically minimizing this function, which is convex. It's a suggestive thing. What is the gradient of this f? Well, the gradient, is a vector that's indexed by sets. And so at the coordinate S, it's the number of uncovered elements in S. Negative, I think, right? Yeah. So I forgot a negative sign. That's fine. Right. So any element that's covered will just be 0. Let's ignore the non-differentiable points. And then every element that is uncovered will contribute like a -1 to sets that contain it. This is proportional to the following. Let's look at like a vector. Excuse me. Let's look at an element, and we're thinking about a particular set. And let's take the x, like the indicator of whether this element, conditioned on being sampled from the uncovered part of the space, lands in that set. This is exactly an estimate of this gradient, right? Let me let you stare at this for a second. It's like scaled, but otherwise like unbiased estimate of this gradient. So, okay, one more time. So I'm sampling an element uniformly at random from the uncovered elements, and then creating a bit vector where that has like set number of sets, many coordinates. And then every coordinate of this vector is 1 if that set contains that element. And then I'm taking the expectation over all such elements. That's a gradient, basically. That's a stochastic gradient. And so in fact, we can think of random order as revealing a stochastic gradient of this function. You can calculate this expected gradient, but only in random order. Somehow this is not available to you in adversarial order. Okay, I wish I could say more. This is really just what I wanted to say. I would love to understand if we're like secretly doing some kind of gradient descent. In fact, we're using the stochastic gradient to do our update. So we are running some kind of, it's a mirror descent if you want to be fancy. We're using this gradient information to do our updates, but somehow like the bounds that we get really depend on the random order, and I don't see how they follow from like known gradient descent bounds, but I would love to like understand this connection better. All right, I'll say a few words about how one does this for non-unit costs. So, okay, I mentioned that we got the exponential time algorithm first, then we spent like a month or two, and we got the unit cost version. And the non-unit cost version turned out to be like significantly harder. So the gradient descent analogy actually breaks down now. Yeah, so the main issue when you're solving this for non-unit cost is that it's no longer enough to count the number of uncovered elements that you see over the course of the algorithm. The number of elements is no longer a good proxy for the cost. You somehow need to take the cost into account. So in the gradient descent thing that I was talking about, it's not the number of like iterations of gradient descent, but it's something else. Okay, so I'll just like flash the algorithm. We're not going to go into it in too much detail. It felt wrong to call k the cost of opt when the cost of opt can be a fraction. So I changed the letter to beta. And then we'll define kappa v to be the cost of the cheapest set covering v. So every element v has some cheapest set covering it in the weighted setting, and let kappa v be that cost. The algorithm is very similar to before, with some like modified version of the sampling and the update rule. Okay, so it's a little bit more complicated, the normalization more complicated, and then the backup part where we used to buy an arbitrary set to cover v. Now we're going to buy the cheapest set to cover v. There's a new potential to go along with this new algorithm. We're no longer using the vanilla KL divergence, but we use like a weighted analog of the KL divergence, which is also somewhat standard. And then instead of log of the number of uncovered elements remaining, we're essentially using log of the sum over the uncovered elements of kappa v. So the sum over the elements of the cheapest way to cover that element. And then some betas to, which is the cost of opt to kind of make the scaling work out. And the main idea behind this new thing is that we're tuning both the learning and the sampling rate as a function of this kappa v. And this part is like somewhat new. So it's somewhat standard in online set cover, like in the adversarial version, when you're doing kind of the update rule for the weighted setting, usually you take this, the learning rate. Where's this the pointer? So the multiplying by e becomes multiplying by e to the 1 over c. Cost of that set, right? We're giving a boost every set. We want to take into account the cost of that set. What's somewhat new is the kappa v in the numerator. Okay, and this has kind of a double effect. So one thing that it does is that it makes the potential decrease by something on the order of kappa v. And it also makes the cost of the algorithm on the order of kappa v. So the cost of the cheapest set to cover v is kappa v by definition, but also the sampling, like we've done it in a way such that in fact we've like scaled down our sampling. We've made it much more gradual in such a way that we're always sampling in such that the expected cost of sampling is something like kappa v. So we'll get like 2 kappa v in the expected cost. And simultaneously, we've tuned the potential to kind of match this. So we get that, change in potential is roughly, negative change in the cost of the algorithm. And then a similar analysis to before will let us claim the bounds that we claim. Okay, I think that's basically it. Yeah.
Like, let's say I don't care about poly time.
Yeah.
And I want to do the exponential time. Like, would it just correspond to me sampling the set, proportional to its cost or something like that? Or what would happen?
We tried that. So the first thing we tried was we had this really clean. Oh, sorry. Oh, you asked it. Good. Yeah, we don't know how to make the exponential time version work for costs, actually. It's not enough to sample like proportional to your bang per buck. Yeah, we can come up with instances where this sort of breaks. I mean, yeah, surely like maybe there's a way to do it, but yeah, we couldn't think of it. So also like enumerating the set of things that could be opt is now cumbersome because it's no longer, m to the k. There's no longer m to the k options. It's some like weird knapsack problem, and you have to count the number of these solutions. It's somewhat unwieldy. Yeah. One thing we tried is like maybe you guess both the cost of opt and the cardinality of opt, and then enumerate, still m to the k, but it's not clear that guess and double will get you the cardinality of opt. Yeah. Any other questions? Okay. Good. So yeah, I have a lot of time left, but let's briefly talk about like extensions and lower bounds. So this is the theorem that I claimed at the beginning. So in fact, we show a stronger thing. We show that for pure covering IPs in random order, we can get this log mn bound. And this is really the full theorem that we prove. We also show like a collection of lower bounds, and their starting point is this theorem that we show. We show that you can't do better than log n times log m for a batched version of set cover in random order. And when I say batched, I mean the following. So an adversary is going to decide on some batches of elements to feed me. And those batches are going to arrive in random order. Every time a batch arrives, you have to pick enough sets to cover the entire batch. So you might wonder, is this easier or harder than like the 1-by-1 version? It's sort of not immediately clear that it should be harder. You could imagine you get kind of more information in one go when you get a whole batch, but actually it is harder. And the reason is that you're not getting the batch in random order. Like within the batch, yeah. Okay, I don't know if that explanation made sense, but anyway, it's harder. And this allows us to show a few kind of nice corollaries. You can wonder if you can relax the random order assumption, or is it truly necessary? So one way to relax the assumption is to say, okay, you'll get a distribution on permutations that is not full entropy. So right, the uniform distribution on permutations is the full entropy distribution. It has entropy roughly n log n. Can you get a bound that decays with the entropy of this arrival order distribution? We show that in some sense, not really. So what we show is that there exist distributions over permutations with almost full entropy, 1 minus epsilon times n log n, such that you lose epsilon times log n times log m. So if epsilon is a small constant, then you get, you lose log n log m. This might just mean that entropy is the wrong way to quantify farness from being random order. Maybe there's more interesting ways. And, yeah, and I'm interested in these questions a lot, but this is what we show. The second thing that we show is that for like a much harder problem, which is known as submodular cover, you will lose 2 logs as well. So there's like a hierarchy of harder and harder covering problems you can think about. And in this like very hard one, you will lose log m times log f of n. And this is a parameter that I haven't defined of submodular functions, but it's like a standard kind of measure of volume of submodular functions. Okay, it's a nice question if this bound can be matched. The best bound known is a paper of mine with Anupam from a year ago, which gets log of m times log n times this volume parameter. And the question is, I guess, if you can move the n into the other log. yeah, in this lower bound, m and n are polynomially related. So you can think of this as log mn. Okay, any questions about these? Okay, yeah, so there's lots of future work that we're interested in. So, we think we've discovered kind of a cool new tool, and we want to find out if it lends itself to other problems. As I said, there's this hierarchy of covering problems you can think about, and we're working on these extensions. We're actively working on this. Can you go beyond covering programs? Can you do something better for random order network design questions, for various like matching questions? You can kind of go to town. Is there some like unified theory here of random order online algorithms? Can you reinterpret old results in this like learn or cover framework? These are all questions I'd like to answer. Okay, thanks. I'm done early, but yeah, I'll open the floor to questions.